You can imagine our universe as a giant cosmic ship that keeps expanding in all directions. But even after decades of research, one key question is still open. How fast is this expansion actually happening? It may seem like scientists solved this long ago. Yet for more than 10 years, a single mystery has been challenging modern cosmology. It's known as the Hubble tension, a disagreement between the two most reliable ways of measuring the expansion rate of the universe. And if this disagreement is real, it could mean that our entire cosmological model is incomplete. Let's start with the basics. The Hubble constant tells us how fast galaxies move away from us as space stretches. It affects our estimate of the age of the universe, the formation of galaxies, the growth of cosmic structures, and even the ultimate fate of everything that exists. Today, scientists use two main methods to measure it, and they don't agree. The first method studies the nearby universe, using Cepheid stars and type Ia supernovae. This cosmic distance ladder gives a value of about 73 kilometers per second per megaparsec. It relies on carefully calibrated steps, each one building on the previous. And over the years, this approach has become incredibly precise. The second method looks at the early universe, using the cosmic microwave background. The ancient light released just 380,000 years after the Big Bang. Based on the standard cosmological model, this method gives a different value, around 67. It describes a smoother, slower expanding universe, one with different physical conditions in its earliest moments. 6 units may not sound like a lot, but in cosmology, it's enormous. These measurements define the very scale of the universe. If one of them is wrong, our understanding of cosmic history shifts. If both are correct, then something fundamental is missing from our theories. Because of this, many scientists suspect something deeper is happening. Possible explanations include early dark energy, unusual neutrino properties, modified gravity, or even additional spatial dimensions. These ideas could reshape the foundations of physics, but none have been confirmed. To break the deadlock, we need a third, independent method, one that doesn't rely on supernovae or early universe physics. And such a method exists. Gravitational lensing with time delays. Imagine a massive galaxy between us and a distant quasar. Its gravity bends space, splitting the quasar's light into several paths. Each path has a slightly different length, so changes in the quasar's brightness reach us with small time delays. These delays act like natural cosmic rulers, revealing the geometry of the universe and allowing scientists to calculate the Hubble constant without relying on any previous calibration steps. Recently, an international team studied 8 of these lensing systems. They used data from ground-based observatories, the Hubble Space Telescope, and the extremely precise James Webb Space Telescope. With this combined data, they built detailed models of the lensing galaxies and measured the time delays with high accuracy, higher than what was possible even a few years ago. And the result was striking. The gravitational lensing method produced a value of about 73, matching the local universe measurement and contradicting the early universe result. This strengthens the idea that the Hubble tension is real. It suggests that we may be seeing hints of new physics, something that influenced the early universe in a subtle but measurable way. A hidden component of energy, an unexpected behavior of matter, or a property of space-time we haven't yet discovered. But the work is not finished. Right now, the lensing method has a precision of about 4 to 5%. To draw a final conclusion, scientists need to reach 1 or 2%. The biggest challenges are modeling the mass distribution inside galaxies and expanding the sample of known lensing systems. And that's where the next generation of telescopes comes in. The Vera Rubin Observatory will scan the entire sky again and again, discovering thousands of new variable objects. James Webb continues to observe distant quasars with unprecedented clarity. And the Euclid mission is designed to map the geometry of the universe on the largest possible scales. With these new observations, we may finally learn whether our cosmological model needs a major revision, If future measurements continue to point toward a value near 73, it will be a clear sign that something fundamental is missing from our understanding of the universe. We are living in a remarkable scientific moment. For years, cosmology looked almost complete, a neat picture explaining nearly everything.
But now, one key parameter, the expansion rate of the universe, gives different answers depending on how we measure it. The Hubble tension is not just a technical problem, it's a challenge, a clue, and perhaps the first step toward a deeper theory of the cosmos. And in the next few years, we may witness one of the most important scientific shifts of our time.